Welcome back to the Deep Dive, your shortcut to being well informed. You know, for decades, the semiconductor industry, it felt like it operated under this pretty simple mantra, right? Moore's Law. We were always chasing smaller, faster transistors, mostly for PCs, maybe servers. But if you're tracking the industry today, I mean, you know that whole equation has just changed.
Completely. The ground's really shifted. We're looking at a major inflection point, and it's not being driven by the desktop anymore. It's this explosion of connected devices all around us. So today we've gone through a serious stack of sources, really focusing on these big market trends and the absolutely pivotal role of RF technology radio frequency, plus the massive shifts happening right there on the fabrication floor. Our mission for you listening in is to really get a handle on this defining market shift, what they're calling the ICAPS revolution, and also understand the dual role RF plays. It's fundamental, both inside the chips themselves and maybe a bit counterintuitively as the energy source that actually makes those chips.
Yeah, that dual role is fascinating, isn't it? It's like technology feeding itself. And if we connect this to the bigger picture, the central idea driving all this change is what the industry has kind of branded ICPS. So I is for IoT, C for communications, A for automotive, P for power, and S for sensors. This whole revolution, it means we're prioritizing something more like multidimensional innovation. We're not just shrinking transistors anymore. We're integrating highly specialized analog functions, even mechanical functions sometimes. Think RF front ends, high power switches, radar, sensors, often all onto single substrates.
Right. And the scale of this new market, I mean, that's what's forcing the industry to fundamentally change its approach. The sheer volume is just staggering. Our sources point out analysts are predicting we'll hit nearly 30 billion connected IoT devices by 2027. That's everything from industrial sensors to, medical gadgets.
Exactly. And this isn't some far-off projection. It's happening right now. Those specialized segments, IoT, automotive ICs, they're projected to grow at CAGR, over 13%. That kind of massive diversified volume, demanding high reliability, often low power. It means the old focus on just pure scaling, it's just not enough anymore. The industry really has to master new materials, complex integration schemes. It's a different game.
Okay, let's unpack that demand side a bit more. Starting with what might be the hungriest customer right now, the automotive sector. Modern cars, especially with things like ADAS, self-driving features, and obviously electric vehicles, they use, 2 to 3 times more chips than a standard gasoline car did just, 5 years ago.
Yeah, easily.
Yeah.
A key thing here is what kind of chips those are. It's not just the smart digital stuff. A really significant chunk, maybe 30% to 40% of automotive semis are these wide band gap power devices.
Yeah.
Silicon carbide, CUG, or gallium nitride, GaN. These materials are just essential because they handle the super high voltage, the heat that EVs and fast charging throw off much, much more efficiently than regular silicon can.
Okay, so there's this critical need for cystanescence and gallium. But based on what we read, this creates an immediate and sounds like a painful manufacturing challenge. Why are these materials so hard to deal with in let's say, a traditional silicon fab?
Well, because they really push the limits of standard equipment. Normal silicon processing, it's optimized for, relatively soft materials, lower thermal budgets. Singing, for instance, needs incredibly high temperature growth, epitaxial growth, often way over 1,500 degrees Celsius, just to lay down the films properly. That kind of heat can literally damage standard deposition tools, and it demands ultra-stable, super clean process conditions. Otherwise, you get these tiny crystal defects that just kill the power device. Plus, etching these materials, it's like trying to drill through granite with a plastic bit, basically. They're incredibly hard. So you need aggressive, specialized tools just for etching. This forces fabs to optimize processes across this incredibly diverse range of nodes. You've got legacy lines, maybe well over 100 nanometers for some singy specs, running alongside advanced logic down below 7 nanometers. Logistically and from an equipment standpoint, what's a nightmare?
Speaking of integrated nightmares, let's talk sensors.
Yeah.
Every single IoT gadget, every phone, every car relies on MEMS, right? Microelectromechanical systems, accelerometers, gyros, image sensors.
Exactly. And this brings up a really interesting question. How do you actually manufacture something mechanical, something that physically moves right next to highly sensitive analog to digital circuits, and then package it all together efficiently and reliably? These components, they need really complex process steps like deep silicon etching, often using that famous multi-step Bosch DRI process. And then you need complicated wafer scale packaging afterwards.
Wow. So chip makers are basically tasked with blending analog circuits, digital logic, RF functions, power modules, and mechanical sensors all into one system. That sounds like the definition of a process integration challenge.
It absolutely is. And if you think about it, right, to get that tiny MEMS gyroscope, or that high-power CC switch working reliably, you need unbelievable precision. We're talking nanometer scale. And this is where we pivot to that dual role of RF we mentioned earlier. The irony is pretty stark. The technology enabling these specialized chips to talk to the world, the RF signals, is also the energy source powering the tools that build them.
Okay, let's tackle the first role then. RF in the chip, the connectivity part. The growth numbers here are just undeniable. We're seeing projections for the RF semiconductor market exploding, right? From around $25.7 billion this year, 2024, to over $41.6 billion by 2030. And that growth seems entirely powered by things like global 5G rollouts, all this ubiquitous IoT connectivity, and increasingly sophisticated automotive radar systems.
Yeah, that makes RF circuit design absolutely central to almost everything we do now. You're designing components, amplifiers, filters, antennas, entire transceivers that have to work reliably at really high frequencies, sometimes way up into the millimeter wave band.
Yeah.
You have to integrate these complex front ends, like say your phone's 5G radio or your car's Bluetooth unit, directly onto silicon or maybe specialized compound substrates like silicon, germanium, SIG.
But the need for low-power IoT seems to be pushing a different design strategy, though. It doesn't sound like RF functionality is always chasing the absolute smallest, most advanced process nodes. Is that fair?
Absolutely fair. That's the classic design compromise you see. If you want an IoT sensor that needs to run for 5 years on a tiny coin battery, well, power consumption is everything. So these low-power chips often leverage analog and mixed signal techniques, but on mature nodes, maybe 28 nanometers, 55 nanometers, because frankly, they're cheaper and often offer better power performance for certain analog components. To hit that specific power performance sweet spot, we're actually seeing rapid development of what they call RF-optimized versions of standard processes like 28, 22, even 16 nanometer variants, specifically built just to make better low-power radios. And then, of course, you have specialized cases like automotive millimeter wave radar ICs. They need sub-100 gigahertz RF design. That often means you have to use specialized silicon, gallium arsenide, or SIG processes because standard CMOS just can't handle those speeds efficiently. So yeah, the design choice is completely dictated by the specific ICAPS application.
Okay, so that's RF as the sort of language of the chip, the communication method. Now let's shift to that second, maybe more abstract role. RF as the tool, the physical power source driving the whole fabrication process. This feels like the hidden engine, right? The technology that lets us actually make features measured in atoms.
Right. This is where it gets really deep. Forget the chip design for a second. Many of the most critical steps in actually making a chip, etching patterns, depositing thin films, cleaning wafers, they rely entirely on RF energy, specifically using RF to generate and sustain plasma inside the process equipment. You can almost think of RF power delivery in a modern fab, like controlling the climate inside a super sensitive chemical reactor. The stability, the purity of that RF power, it's absolutely non-negotiable.
Okay, break that down a bit. What's actually happening inside that chamber when the RF is on?
So you have these RF generators, often running at standard frequencies like 13.56 megahertz, maybe 27.02 megahertz. They essentially pump energy into a gas inside the chamber, creating a plasma, basically an ionized gas. This plasma provides the reactive species for chemical vapor deposition, or it provides ions that get accelerated towards the wafer surface during etching. The plasma's consistency, its density, the direction the ions move, it's all directly controlled by the RF power level, the frequency, and something called the matching network, which ensures the power gets delivered efficiently.
Wow. So any tiny variation, any glitch in that RF power translates immediately into potentially catastrophic defects on the wafer.
Precisely. The level, the purity, the stability of that RF power are absolutely critical for getting uniform results across the wafer and achieving selectivity, etching one material but not another. Any spurious signals, any little harmonic interference, it affects the energy distribution within that plasma.
And that directly impacts the quality of the nanometer scale features you're trying to create.
I mean, if you're trying to etch a perfectly straight 7 nanometer line, you need almost perfect control over the electromagnetic field driving that reaction. It's that sensitive.
Okay, let's make this concrete. Tie it back to our ICAPS challenges.
When we're talking about creating those deep trenches for MEMS devices or etching really tough materials like silicon carbide, what specific RF-driven processes are absolutely essential? Well, we rely heavily on techniques like reactive ion etching, or RI. RI uses an RF plasma to create reactive chemicals, but it also applies an RF bias directly to the wafer holder, the substrate. The crucial part here is that this RF bias accelerates ions vertically, straight down towards the wafer. That gives you that directional or anisotropic etch profile, sharp vertical walls. That ion bombardment is what lets you create these deep, sharp features without undercutting the pattern vital for those complex MEMS structures we talked about.
And what about for ultra-precise deposition, like those high dielectrics needed for the most advanced logic transistors?
For that level of control, you generally need atomic layer deposition, ALD. It's amazing stuff. Lays down films literally one atomic layer at a time. ALD is super sensitive to temperature and surface conditions. So, often, to ensure you get perfect conformality, meaning the film coats everything evenly, and perfect thickness control, we use specific RF plasma steps. Maybe to activate the chemical precursors at lower temperatures, or sometimes just to clean the surface perfectly between those atomic layer pulses. The RF plasma basically ensures the film goes exactly where it's supposed to, layer by layer, eliminating those tiny pinholes or defects that would ruin performance at the atomic scale.
Okay, and when you need really high volume, deep structures, you mentioned those deep silicon trenches for MEMS gyroscopes, you usually turn to inductively coupled plasma etch, or ICP, right?
Yeah.
How does RF play in there?
Right, ICP is kind of the powerhouse for deep etching. It uses a separate RF coil, usually wrapped around the chamber, to create a very high-density plasma, much denser than standard RE. Critically, this plasma generation is separate from the RF bias applied to the wafer chuck itself, similar to R. So when you combine that high-density plasma from the coil with the directional ion acceleration from the RE bias on the substrate, that's how you achieve those extreme high aspect ratio etches. Really deep, narrow trenches for MEMS or for through silicon vias, TSVs. But you need perfect RF power synchronization and control between those two RF sources, the coil and the chuck bias, to maintain that etch profile, all the way down through hundreds of microns of silicon.
That paints a really powerful picture. The RF signal in the chip defines connectivity, and the RF energy in the tool defines the physical precision. And all this specialization, all this need for precise RF control for different materials and structures must be driving a global equipment race. Which brings us neatly to the geopolitical context. Our sources spent some time highlighting India, which seems to be rapidly positioning itself as a major emerging hub in this space. Backed by significant government muscle, significant investment, specifically aiming to capture a piece of this ICAPS market.
Yeah, India is definitely making major policy moves. The government kicked off this huge $10 billion semiconductor mission. The goal is explicitly to establish local chip fabs, packaging facilities, OSATs, and also R&D centers. And importantly, this isn't just a generic investment in chips. It seems very strategically aligned with these specific ICAPS demands we've been talking about.
How so? How does that investment align specifically with the RF needs and specialized chip demands we just discussed?
Well, it aligns perfectly, actually. India's own domestic market is booming in key ICAPS areas. Think about the massive government push towards electric vehicles, the rapid and frankly huge 5G network rollout by carriers like Jio and Airtel, plus large smart city projects, IoT infrastructure initiatives. These are precisely the markets that need RF front ends for connectivity, specialized MEMS sensors for all sorts of applications, and those high-power SiAS and GaN devices for EVs and power grids. So this means India will be aggressively sourcing the kind of specialized equipment we just talked about. The RF-optimized 28mm tools for IoT radios, the high-power SiC processing tools. Basically the gear that the rest of the world is developing right now for these applications. So if you look at the global picture, this strong policy support, combined with a large and rapidly growing domestic electronics market, it means India is going to be an increasingly critical player in the global chip-making story. And they will absolutely require advanced RF-driven equipment for pretty much every ICAPS technology we've defined today.
Okay, so let's try to summarize our deep dive today. We've really identified two massive transformations that are simultaneously reshaping the entire semiconductor industry. First, the market itself is dictating a whole new type of chip. It's this revolutionary shift towards ICAPS, moving away from just pure scaling, Moore's law, and towards what you called multidimensional innovation, specialized functions, new materials.
Exactly. And second, radio frequency technology emerges as this kind of invisible thread connecting both the design and the manufacturing. RF circuit design enables the connectivity, the sensing, the communication on the chips themselves, while RF-powered plasma provides the absolutely necessary precision for the incredibly complex etching and deposition steps required to physically build those next-gen devices, especially with challenging materials like seed-rike and GaN. So for you listening, whether you're tracking market trends or maybe you're working right there on the process floor, the key takeaway, I think, is that the future of fabrication isn't just about speed anymore. It's increasingly about control. exquisite control. It means innovating deeply in areas like RF delivery systems, plasma uniformity control, advanced materials integration, all to service this high-growth, highly diversified ICAPS landscape.
That raises a phenomenal point about control, because everything we've talked about, the future of EVs, global 5G connectivity, those, 30 billion connected devices, it all depends entirely on creating these incredibly tiny nanometer scale features with near perfection. So here's something I want you to consider, just mull over.
Yeah.
If the final ultimate precision required to power our entire connected world, if it comes down to achieving absolute pristine stability in something as fundamentally abstract as controlled radio frequency plasma energy, what does that really tell us about the future constraints or maybe the future opportunities of technological advancement? Something to think about. That's all the time we have for this deep dive. We'll see you next time.